I stood before a machine rewriting everything we know about engineering. The 800 meganewton press in Deyang, China, the most powerful machine ever built by humanity. 80,000 tons of pressure. Picture 1,000 Eiffel Towers simultaneously crushing down on a single piece of metal. This monster packs 30,000 tons more force than America's strongest press and 10,000 more than Russia's. Without it, China wouldn't have launched its heavy Long March rockets or built the world's largest aircraft. Today, I'm taking you inside this metal fortress. Ready to see the absolute limit of what's possible? When the tour bus pulled up to the Erchong factory in Deyang, I thought there'd been a mistake. Stretching out before us was a building the size of a football field, but as tall as a 25-story skyscraper. Our guide smiled. Welcome to the home of the most powerful machine on the planet. We walked inside through massive doors 3 feet thick, and I felt it immediately. This was a different scale of reality. The place is so huge it creates its own weather inside. Clouds of steam from the metallurgical processes hung beneath the ceiling. The temperature fluctuated. Near the furnaces it hit 100 degrees Fahrenheit, by the cooling systems 80. And then I saw it. The 800 meganewton press stood in the middle of the workshop, and the word monster seemed insultingly small for this structure. Imagine 4 80-story skyscrapers stacked on top of each other and compressed into a metal frame. The press stands 132 feet tall. That's taller than the Statue of Liberty without the pedestal. The guide started rattling off numbers, and I could barely keep up with my notes. The press itself weighs 72,000 tons. That's more than a U.S. Nimitz-class aircraft carrier. But unlike a carrier, where that weight's spread out over 1,000 feet, this mass is concentrated in an area just 150 by 100 feet. The pressure on the foundation is so immense that beneath the press they poured concrete 50 feet deep. 80,000 tons of force, the guide said, pointing at the main hydraulic cylinder, 9 feet in diameter. You know what that means? I shook my head. It means if we stacked 1,000 Eiffel Towers on top of each other right here, their combined weight would equal the force of a single stroke from this press. To really grasp the scale, let's compare it to something I'd seen before. Tesla's Gigapress, the one everyone talks about, delivers 9,000 tons. That's impressive. That's a revolution in car manufacturing, but next to 80,000 tons? It looks like a toy. If the Gigapress was a pocket knife, this Chinese press is a 6-foot-long samurai sword. America's Mesta 50, the legendary Cold War press, clocks in at 50,000 tons. An impressive machine that keeps American skies flying. But the Chinese press is 30,000 tons more powerful. This isn't just bigger, it's a whole different level of physical capability. The guide walked us to the press's foundation, 4 steel columns holding up the entire structure. I stepped closer and pressed my palm against one of them. Steel cold, dark gray, with barely visible machining marks. Each column's diameter, 12 feet. That's the width of a 3-bedroom apartment. The columns are hollow inside, but with 18-inch walls made from steel that handles 350,000 pounds per square inch. How did you even build this thing? I asked. An engineer who'd joined the tour smiled. This was the most complex engineering challenge in China's history. We started in 2005. He tells an incredible story. The columns were manufactured at a different plant, 300 miles away. Each one weighed 5,600 tons. To transport them, the Chinese built a special railway line and a platform with 240 axles. The train moved at 3 miles per hour. Transporting each column took 6 days. When the columns arrived at the plant, a real battle with gravity began. China's largest crane, with a lifting capacity of 10,000 tons, raised each column vertically. The process takes 36 hours per column. Workers operate around the clock, monitoring every millimeter of the lift. If a column tilted even 3 degrees, it would fall, and the catastrophe would destroy half the plant. When all 4 columns were in place, they connected them with a top crossbeam, a beam 150 feet long and 8,000 tons. This beam was so massive they shipped it by sea from Shanghai. Installing the beam took 2 months. Then came the installation of the hydraulic systems. The The main cylinder, 9 feet in diameter, contains a piston that moves at 4 inches per second. When 80,000 tons move at that speed, the kinetic energy is so massive it could tear ordinary steel apart. That's why the cylinder is made from a special alloy developed specifically for this press. Surrounding the main cylinder are 8 auxiliary ones, each 4 feet in diameter. They don't create the main pressure, they stabilize it, ensuring even load distribution. The total amount of hydraulic fluid in the system? 18,000 gallons. That's almost 2 full tanker trucks. Finally, they took us to the observation deck overlooking the work area. That's where the magic happens. I watched as they wheeled a workpiece up to the press, a titanium ingot weighing 9 tons. It had just come out of the furnace and glowed bright yellow, 2,000 degrees Fahrenheit. A robotic arm carries the glowing titanium into the lower die. The upper die descends from above. Each one weighs 300 tons, and then everything goes still. 3 seconds of silence. Hydraulic pumps build pressure, and then impact. 80,000 tons slam down onto the metal. The sound is incredible, not an explosion, but a deep, visceral roar that you don't hear with your ears but feel with your entire body. Vibration travels through the concrete floor, rises up your legs, resonates in your chest. I instinctively grabbed the railing. Under that insane pressure, titanium behaves like a liquid. It flows, filling the mold, streaming into the thinnest channels. In 4 seconds, a 9-ton block transforms into a support beam for the fuselage of China's largest passenger aircraft, the C919. A part 42 feet long, but only 9 inches thick at its thinnest points. Why so much force? Someone from the tour group asked. The engineer walked up to a diagram on the wall. Look, this is the wing spar for a Boeing 787, 37 feet long. The Americans forge it from an alloy that needs 50,000 tons of pressure. Our C990 is bigger. Wing spar's 53 feet, 80,000 tons. He pointed to another image. And this is a component for the Long March 5 rocket. It can lift 25 tons to geosynchronous orbit. Engine nozzles 10 feet across. Only way to forge something like that is here. I stared at the press and understood. This wasn't just a machine. This was a claim to technological leadership. The US has a 50,000-ton press. Russia has a 75,000-ton press. But China went further. 80,000 tons. That's the limit of what humanity can do with steel and hydraulics right now. The guide shares one final detail. Power consumption for a single strike, 2 megawatts. That's what a small town of 10,000 people uses. When the press fires up, voltage across the entire plant drops 5%. The statistics are staggering. The press runs 24 hours a day, but only delivers 8 to 10 strikes per day. Each strike requires an hour of prep, heating the workpiece, installing the die, checking the system. But each component is worth $100,000 to $500,000. Over 10 years of operation, the press has forged more than 2,000 mission-critical parts. Without them, China wouldn't have its own wide-body aircraft, wouldn't be launching heavy satellites into geostationary orbit, wouldn't be building third-generation nuclear reactors. When the tour ended, I stood there for another 5 minutes, just staring at this giant. 72,000 tons of steel, capable of generating 80,000 tons of force. 300 engineers maintaining one machine. 10 years of construction, $3 billion invested. This isn't just a press, it's a symbol of how far human engineering has come. We've learned to take the hardest metals on the planet and transform them into the most complex shapes with a single strike. We build machines that weigh as much as an aircraft carrier to make parts for machines that fly into space. And the most incredible part? This isn't even the limit. Engineers are already designing a 100,000-ton press. When it's built, humanity will once again push past the impossible. Subscribe so you don't miss that story. But for now, 80,000 tons is the peak, the absolute champion, the most powerful machine humanity has ever created. We're in Turkey, on the shores of the Dardanelles Strait, and what you see behind me is officially the longest suspension bridge on the planet. The Canakkale 1915. Its center span, exactly 6,637 feet of symbolism and engineering audacity. When it opened in 2022, That measurement allowed the bridge to surpass Japan's Akashi Kaikyo and become the longest suspension bridge in the world. But here's the thing, it's not just about length. Look at this roadway. It's not concrete, it's pure steel. Today, I'm going to show you how, at the Ximtus Steel Factory, they welded together entire chunks of continent that were then hung over the abyss like building blocks. Let's go! To build this giant, engineers decided to ditch traditional methods. They headed to the Ximtus steel plant in Gemlik. Here, steel isn't just cut. Here, they create mega blocks from it. Picture this. Instead of assembling beam by beam up in the air, the guys at the factory welded together a ready-made chunk of road. One block like this measures 157.5 feet long, 147 feet wide, and 6 feet tall. That's the area of 2 professional basketball courts, welded into one monolith. A single block weighs 700 tons. That's like lifting 5 Boeing 747 passenger jets into the air all at once. When you stand in the workshop next to this beast, you don't see a bridge, you see a steel skyscraper laid on its side. At the heart of this bridge lies what's called an orthotropic steel deck. Simply put, it's a hollow steel box. But what a box! Inside, this block resembles the compartments of a submarine. Every millimeter of the structure is airtight. There are miles of welding seams running through here. A true symphony of sparks. At Ximtus, they used robotic portals that welded steel 24/7. Why such complexity? Because inside the block, a special microclimate is maintained. It's as dry as the Sahara Desert in there, so rust can never reach the heart of the structure. This is eternal steel that doesn't fear the humid sea air of the Dardanelles. When you peer inside one of these blocks, it feels like you've stepped onto a science fiction movie set. Endless steel ribs of reinforcement disappearing into darkness. The welding process starts with the bottom plate. These are massive sheets of special steel laid out on a perfectly flat magnetic floor. But the plate by itself? Just iron. To handle the weight of thousands of trucks, it needs reinforcement. That's where the stiffeners come in. Long steel channels running the entire length of the block. How do you weld them? By hand, it'd take a decade. So instead, a massive portal rolls over the plate. An automated welding station. It looks like science fiction. Dozens of welding heads descending to the metal simultaneously. They move in sync, like the legs of a steel spider. You see dozens of bright points of light crawling along the plate. This is submerged arc welding with multiple heads. The metal melts beneath a layer of special flux so you don't see open flame, but you feel the air in the workshop rumble from the power of those electric arcs. Once the bottom plate is reinforced, assembly of the sidewalls and partitions begins. This is when the box takes on volume. Diaphragms are installed every few feet inside the section. These are the internal skeletal ribs of the bridge. This is where the hardest work begins. Welders go inside the section. Picture this. You find yourself in a steel maze. Above you, the roof of the future roadway on the sides, walls and all around, just the glint of lamps and the sound of metal. Every joint between the internal ribs and outer shell is welded by hand or semi-automatic machines. Everything matters here. Temperature, humidity, the speed of your hand. Why? Because this block has to be airtight. When the top plate, the actual roadway section, covers this structure, they seal the block completely. It's like building a submarine that's going to hang in the air. If even a little moisture gets inside, it'll start eating the metal from within, and you'll never see it from the outside. That's why after welding, every seam gets checked with a vacuum test or X-ray. If there's even one micro crack, they cut out the weld and do it all over again. The most interesting part is the top plate where the cars will drive. That's the orthotropic deck itself. It's a steel plate welded with longitudinal and transverse ribs so that it's incredibly rigid in one direction and slightly flexible in the other. When you look at a finished mega block from the outside, it seems smooth and black after painting. But inside, it's a true lacework of steel. Miles of welds. If you unraveled all the welding seams from one of these blocks into a single line, it would stretch for dozens of feet. And every inch of that line has to withstand the vibration from the wheels of millions of cars over the next 100 years. After the last seam is completed, the block goes to abrasive blasting. The steel is literally bombarded with tiny metal balls to remove scale and prep it for painting. Then, several layers of protection, and these 700 tons in one piece are ready for their journey by sea. Are you ready to subscribe to this channel? Do it now. We move on to the key stage of assembly, lifting the sections. The completed mega block is delivered to the Dardanelles Strait on special pontoons. At this point, all shipping in the strait comes to a complete halt, because the operation demands perfect precision without interference from waves created by other vessels. For the lift, one of the most powerful floating cranes in the world is used, the Asian Hercules III. This vessel is technically a self-propelled heavy-lift floating crane, capable of lifting up to 5,000 tons. To put that in perspective, its hull is over 300 feet long. Its job is to approach the pontoon with the section, secure it, and lift it to the design height of roughly 250 feet above sea level. The lift itself is pure math. The mega block's weight gets distributed across multiple attachment points to avoid any tilting that could warp the steel box. The crane operates at low speeds to minimize wind load impact, which at this height is a critical factor. When the section reaches the right level, it connects with the suspenders running from the bridge's main cables. This is the moment load transfers from the crane to the bridge structure itself, requiring perfect synchronization of all hydraulic systems. Since Turkey uses the metric system, this bridge is packed with symbolism. The length of 2,023 meters is a direct nod to the year 2023, the centennial of the founding of the Turkish Republic. The height of the towers isn't random either, 1,043 feet. These numbers symbolize the date March 18th, meaning the 18th day of the third month, the day of victory in the Battle of Canakkale in 1915. The total length of steel wire used for the main cables exceeds 531 million feet. That's enough to wrap around the Earth at the equator 4 times. The steel roadway deck alone weighs close to 50,000 tons. The total weight of steel in the project exceeds 100,000 tons. And for the foundations and towers, 8 million cubic feet of concrete was used. That's a volume that could fill a small town with 2-story houses. Don't ask me why the example of filling a town with concrete popped into my head. The Dardanelles Strait is characterized by high seismic activity and extreme winds, so engineers built colossal safety margins into the design. The bridge is engineered to withstand wind gusts up to 174 miles per hour. This was made possible through a split road deck. 2 separate steel box girders have a gap between them, allowing powerful air currents to flow freely through the structure, virtually eliminating the sail effect. As for seismic protection, the bridge supports are based on massive steel caissons installed on the seabed. To ensure stability, the ground beneath them was pre-reinforced with steel piles, 363 of them, each with a diameter exceeding 8 feet. This foundational preparation allows the bridge to safely withstand earthquakes exceeding magnitude 7.0 while maintaining the integrity of all critical connections. Board New York City subway, 5.5 million people daily. You grab the pole, doors close, train accelerates into darkness. The car carrying you weighs 85,000 pounds, contains 20 miles of electrical wiring, 10,000 individual components, and required 6 months to build. This 60-foot steel box began as flat sheets in Nebraska cornfields, traveled through 2 factories across 1,200 miles, and survived testing that would destroy ordinary vehicles. One company builds every new NYC subway car, Kawasaki, operating facilities in Lincoln, Nebraska, and Yonkers, New York. How does 40 tons of steel become underground transportation for millions? Why does single subway car cost $3 million? Stay with us. We'll witness welding robots joining steel with surgical precision and discover Subway's shocking secret: the air hockey floor that lets 2 workers move 85,000-pound train car by hand. Kawasaki Motors Manufacturing in Lincoln, Nebraska occupies 733,000 square feet. Facility so large you could fit 12 football fields inside. This plant produces subway cars for New York, Washington, D.C., and other major cities. For NYC's R211 order, Lincoln operates 3 dedicated production lines running 24/7. The facility manufactures 22 cars monthly, 1 complete subway car every 33 hours. Walk the receiving dock where flatbed trucks deliver stainless steel sheets from Arcelor Middle and Nucor mills. Each sheet measures 12 feet by 40 feet, weighs 800 pounds. 1 subway car requires 50 steel sheets totaling 40 tons. The factory floor operates on technology found nowhere else in North America: air bearing system. The entire floor contains thousands of tiny holes releasing compressed air, creating cushion between floor and work platforms. Each 85,000-pound subway car sits on platform floating on air film thinner than credit card. 2 workers can push entire car anywhere in facility. The floor stays so flat, tolerances within thousandths of inch that it resembles polished mirror. This system provides ultimate manufacturing flexibility, allowing cars to move between workstations without tracks or cranes. Car body construction begins with laser cutting. German-made Trumpf laser cutters slice stainless steel with 15,000-watt beams, cutting through half-inch steel at 30 inches per minute. The laser follows computer patterns precise to 0.005 inches. Side panels, roof sections, floor plates, end walls. Every piece cut to exact dimensions. Burrs get removed through automated deburring stations. The steel, grade 304 stainless, contains 18% chromium and 8% nickel, providing corrosion resistance for 40-year service life in humid subway tunnels. Welding robots join the pieces. 6 Kawasaki-built robots work simultaneously on single car, each programmed for specific welds. MIG welding, metal inert gas, uses argon shielding preventing oxidation. The robots lay 3,000 linear feet of weld per car, moving at precisely controlled speeds. Watch robotic arm trace floor-to-wall joint. The weld bead forms perfectly uniform, penetrating through both pieces, creating joint stronger than base metal. Welders wearing auto-darkening helmets monitor every joint. One supervisor explains, "Robot makes perfect weld every time, but human checks every inch. We're building transportation for 5 million people daily." The car shell, bare steel skeleton, moves to assembly station where floor installation begins. Plywood subflooring goes down first, providing sound dampening and thermal insulation. Over this, workers install rubber flooring material designed for subway service. Slip-resistant, easy to clean, resistant to chemicals and fluids. The flooring attaches via adhesive and mechanical fasteners every 6 inches. Ceiling panels install next. White fiberglass reinforced plastic reflecting LED lighting. These panels contain 16 air conditioning vents per car, each precisely positioned for optimal airflow. Interior wall panels get mounted to steel framework. Each panel, formed from molded fiberglass, fits specific location. The panels interlock via hidden fasteners, creating smooth interior surface. Behind walls, workers route conduit for electrical systems. Every wire, every cable follows engineering drawings, specifying exact paths. The conduit protects wiring from vibration, moisture, and passenger contact. Installing interior panels on single car takes 12 workers 3 days, 96 man-hours of precision fitting. Electrical installation is where complexity peaks. Each R211 car contains 20 miles of wiring, enough to stretch from Lincoln Factory to downtown Omaha. 3 master electricians and 6 assistants spend 2 weeks per car running wire. The wiring includes power distribution, lighting circuits, door controls, HVAC systems, communication systems, passenger information displays, and CBTC, communication-based train control. Every wire gets labeled at both ends with alphanumeric codes. Color coding follows strict standards: red for positive power, black for negative, green for ground, yellow for control signals. The main electrical cabinet, brain of the car, occupies space beneath seating. This cabinet contains 70 circuit breakers, 40 relays, 12 transformers, and computer control modules. Workers connect each wire to specific terminals, torquing every connection to exact specification. 25 inch-pounds prevents loose connections causing failures. Testing happens continuously. Multimeters verify every circuit. Megohmmeter tests insulation resistance. Must exceed 100 megohms between any circuit and car body. One electrical error could disable entire train, so triple checking is standard procedure. Door installation requires watchmaker precision despite massive scale. Each car has 4 door sets, 8 individual panels. The doors, 58 inches wide, are 8 inches wider than previous generations, reducing station dwell time by 30%. Each door weighs 200 pounds, hangs on aircraft-grade bearings rated for 10 million cycles. Pneumatic actuators powered by 100 psi compressed air open and close doors in 2 seconds. The door edges contain rubber seals preventing finger injuries. LED strips around each door flash green when opening, red when closing. These lights contain 500 individual LEDs per car, controlled by dedicated microprocessor. Seating installation follows specific layout. Blue molded fiberglass seats designed for durability and easy cleaning. Yellow flip seats provide wheelchair space. Grab poles, stanchions, and handrails install according to accessibility standards. The looped stanchions, unique design allowing multiple grip points, get welded to floor and ceiling, tested to withstand 500-pound side load. Digital displays mount above doors. 28 screens per car showing route information, station stops, and service alerts. Each screen connects via Ethernet network running entire train length. After 8 weeks in Lincoln, the car, still incomplete, loads onto flatbed truck for 1,200-mile journey to Yonkers, New York. Multiple cars ship weekly on specialized railcar transport trucks. The Yonkers facility, 250,000 square feet, occupies former Otis Elevator Factory. Here, final assembly transforms Lincoln-built shells into operational subway cars. The facility maintains quarter-mile test track, elevated rails allowing full speed testing indoors. Workers install propulsion systems. Alstom-built Optonix traction motors, generating enough power to accelerate 85,000-pound car from 0 to 50 miles per hour in 30 seconds. 4 motors per car, each weighing 1,200 pounds. The motors connect to trucks, wheel assemblies containing suspension, brakes, and gearing. Brake systems use both pneumatic and electrical braking. Pneumatic provides emergency stopping. Electrical regenerative braking converts motion energy back to electricity, feeding power line. Installing and aligning propulsion system takes 5-person crew 1 week per car. Testing begins before car leaves factory. Static tests verify all electrical systems function correctly. Doors cycle 1,000 times. HVAC runs continuously for 48 hours. Every light, every display, every sensor gets checked. Then dynamic testing, the car runs on indoor test track, accelerating, braking, taking curves at speed. Computers monitor bearing temperatures, wheel alignment, electrical consumption, brake performance. The test track includes curve equivalent to sharpest turn in NYC subway system. Track engineers verify car navigates without derailment risk. 5 car sets get assembled and tested as complete trains. The open gangway R211T models, 20 cars featuring accordion connections allowing passengers to walk between cars, undergo additional flex testing. Workers measure gangway movement through curves, verifying seals maintain integrity. Sound testing measures interior noise levels. Must stay below 85 decibels at speed. Climate testing runs HVAC at temperature extremes. After passing all tests, the train gets final inspection. MTA representatives examine every detail before acceptance. Rejection rate runs 2%. Rejected cars return for correction, delaying delivery. Kawasaki entered U.S. railcar manufacturing in 1982, winning contract for NYC's R62 subway cars. Since then, the company delivered over 5,000 railcars to American transit agencies. The Lincoln facility opened in 2001 specifically for subway car production, utilizing techniques developed building Japanese Shinkansen bullet trains. The Yonkers plant, established in 1986, has produced cars for every major northeastern transit system. Completed R211 cars travel final miles to New York City via their own power or rail transport, arriving at Coney Island Yard or Pitkin Yard for 30-day acceptance testing. Transit workers operate cars on actual subway lines during non-revenue hours, monitoring performance. After successful testing, cars enter passenger service. The first R211A cars began service March 2023 on the A train. Open gangway R211Ts entered service February 2024 on the C line. Eventually, 1,610 R211 cars will replace entire fleets of R46 and R68 cars built in 1970s. Environmental impact shows interesting contradiction. Manufacturing subway car generates approximately 40 tons CO2 emissions, mostly from steel production and electricity consumption. However, one car serving 40-year life transports 100 million passengers, preventing equivalent of 20 million car trips. Net carbon savings exceed 10,000 tons CO2 per car over lifetime. The stainless steel body is 95% recyclable. After 4 decades service, retired cars get shredded, steel returns to mills, becomes new cars. Here's the secret we promised. Subway cars' 40-year lifespan means it outlasts almost everything else humans build. Your car lasts 15 years, your phone lasts 3. But subway car manufactured today will still be carrying passengers in 2065. That's why single car costs $3 million, because every component must survive 40 years of daily violence. Doors opening and closing 50 times per trip, 400 trips daily, 6 million cycles over lifetime. Electrical systems enduring temperature swings from freezing to 100 degrees. Structural steel flexing through millions of acceleration and braking cycles. The engineering isn't just about building strong car. It's building car that stays strong through 4 decades of punishment that would destroy normal vehicles in months. From Nebraska cornfields to Manhattan tunnels, the transformation completes in 6 months. Kawasaki's Lincoln and Yonkers plants represent capability concentration, decades of railcar knowledge, specialized equipment found nowhere else, and workforce expertise impossible to replicate quickly. That R211 carrying you through subway system contains work of 300 workers across 2 states in 6 months. Those 20 miles of wiring, 10,000 components, 3,000 feet of welds, all positioned perfectly, all tested thoroughly, all guaranteed to function for 40 years. You board, you ride, you exit, never thinking about the engineering miracle carrying you. But now you know, nothing about subway car is simple. Everything is deliberate, tested, and built to outlast almost everything else in your life. Tear open your wall. Behind the drywall sits engineered wood, either plywood or OSB-oriented strand board. They look completely different yet serve identical purpose. Plywood, smooth layers of thin wood stacked like pancakes. OSB, chaotic jumble of wood strands compressed together. North American construction consumes 30 billion square feet annually, enough to cover Rhode Island 50 times over. One panel costs $12. The house surrounding you required 300 panels minimum. How does round tree trunk become flat sheet stronger than solid wood? Why did ugly OSB nearly kill beautiful plywood? Stay with us. You'll witness the violent beauty of spinning logs becoming continuous wood ribbons and discover the counterintuitive secret. Wood is stronger when you destroy its natural structure. The mill dominates the landscape, a facility processing 1 million board feet daily. Log trucks arrive continuously, each hauling 40 tons of Douglas fir or southern yellow pine. The debarking drum, 60 feet long and 10 feet diameter, rotates like giant clothes dryer. Logs tumble inside while high-pressure water jets at 3,000 psi blast bark away. The noise resembles continuous explosion. Workers wear double hearing protection. Watch the veneer lathe operation. A peeler lathe grips 8-foot logs at both ends, spinning them at 200 RPM while a knife blade, sharp as surgical scalpel and wide as the log, shaves continuous ribbon of wood. The veneer peels off like paper towel unrolling, emerging as sheet 1/8 inch thick and hundreds of feet long. 20 workers monitor 12 lathes simultaneously. One operator explains, Log spins, knife stays still. Physics does the work. We just remove what breaks. The veneer ribbon, still damp from trees' moisture, feeds through dryers. Conveyor ovens stretching 300 feet. Temperature reaches 350 degrees, reducing moisture from 50% to 6% in 8 minutes. Dry too fast, the veneer cracks. Too slow, production bottlenecks. Sensors monitor moisture content constantly, adjusting heat and speed automatically. After drying, veneer gets clipped into precise sheets, 4 feet by 8 feet, the industry standard. Automated clippers cut at speeds exceeding 1 sheet per second. The clipping produces massive waste. 30% of veneer becomes scraps. But nothing wastes here. Those scraps feed directly to the OSB plant next door. The integration is complete. Plywood's waste becomes OSB's raw material. 1 tree enters, 2 products exit. Glue application transforms loose veneer into plywood through chemistry. Phenol formaldehyde resin, waterproof adhesive surviving decades of weather exposure, gets sprayed onto veneer surfaces. The glue spreads microscopically thin, just 0.02 of an inch. Too much glue costs money and creates brittle joints. Too little, the plywood delaminates under stress. The layup process stacks veneers perpendicular to each other, grain directions alternating 90 degrees between layers. This cross-grain construction is plywood's genius. Solid wood splits easily along grain but resists splitting across grain. By alternating grain directions, plywood eliminates directional weakness. A 5-ply panel, 5 layers total, achieves strength in all directions that solid wood can't match. The stacked sheets, still unbonded, go to the press. The hot press is where plywood is born. Massive hydraulic press, 40 feet square, contains 30 openings stacked vertically. Each opening holds 20 plywood panels. Workers load 600 panels simultaneously, 12,000 square feet entering press at once. The platens close, applying 1,000 psi pressure while heating to 290 degrees. Under heat and pressure, the phenolic resin undergoes chemical cross-linking, molecular chains bonding permanently. The process is irreversible. Once cured, the glue can't melt again. Press time varies by thickness. 3 minutes for 1/4 inch, 12 minutes for 3/4 inch. When press opens, steam erupts as residual moisture flashes. The panels emerge hot, rigid, transformed. What entered as loose layers exits as single engineered unit, stronger than the tree it came from. OSB manufacturing begins differently, with destruction. Instead of peeling veneer, trees get shredded. The strander machine uses rotating disc containing hundreds of knives. Logs feed through, emerging as strands. Thin rectangles 6 inches long, 1 inch wide, 0.025 inches thick. The violence is spectacular, logs disintegrating into thousands of pieces in seconds. These strands dry similarly to veneer but require less precision. Moisture content targets 8%. The dried strands get coated with wax and resin, different chemistry than plywood. OSB uses MDI, methylene diphenyl diisocyanate, bonding faster and cheaper than phenolic. The coated strands look like wood chips covered in syrup. They feed to forming stations where magic happens. Orientation. Orientation differentiates OSB from random particle board. The forming line uses electrostatic alignment or mechanical orientation systems, forcing strands to lay parallel in outer layers, perpendicular in core layer. This mimics plywood's cross-grain structure but achieves it through chaos rather than precision. Picture billions of wood strands, each finding its place in 3-dimensional puzzle. The matte, loose collection of oriented strands 8 inches thick enters continuous press. Unlike plywood's batch press, OSB uses continuous process. The mat feeds into press heated to 400 degrees under 2,000 psi pressure. As it travels through, thickness compresses from 8 inches to 7/16 inch while resin cures. The panel exits as continuous ribbon, cut to length by flying saws. Production speed reaches 600 feet per minute, 1 4x8 panel every 8 seconds. Plywood originated in ancient Egypt. Archaeologists found plywood furniture in King Tutankhamun's tomb from 1300 BC. Modern plywood production began in 1865 when Emmanuel Nobel, father of Alfred Nobel, developed rotary lathe cutting continuous veneer. World War II accelerated development. Plywood construction enabled mosquito bombers, proving engineered wood could replace scarce aluminum. OSB emerged in 1960s Canada as solution to log supply crisis. Small diameter trees and branches, unsuitable for veneer peeling, worked perfectly as strands. Armin Elmendorf at Elmendorf Research created first commercial OSB in 1978. Initially dismissed as cheap substitute, OSB gradually proved equal or superior performance at lower cost. Today, OSB outsells plywood 3-to-1 in North American construction. The ugly duckling became the swan. Carbon emissions comparison favors engineered wood dramatically. Producing plywood or OSB generates 80% less CO2 than steel framing equivalents. Both products sequester carbon. The wood stores atmospheric CO2 for the building's lifetime. Industry plants 3 trees for every one harvested, making this genuinely renewable material. Here's the secret we promised. OSB dominates because it's democratized wood. Plywood requires perfect logs, large diameter, straight grain, minimal knots. Only 15% of logs qualify. OSB uses everything: crooked trees, small diameter, branches, plywood scraps. The random strand orientation means defects disappear into aggregate. That gnarly branch causing plywood failure becomes invisible in OSB's chaos. We learned that destroying wood's structure, cutting it into strands and reassembling randomly, creates stronger, more consistent product than respecting original form. From forest to framing, the cycle completes. We've engineered materials stronger than nature, provided by accepting that perfection comes through controlled destruction. That wall surrounding you isn't wood anymore, it's wood reimagined. It's fibers oriented and bonded beyond biological limits. Plywood taught us to slice and stack. OSB taught us to shred and randomize. Both taught us that human engineering can improve on millions of years of evolution when we stop trying to preserve what nature made and start rebuilding it our way.
Hold a car battery. It weighs 40 pounds. 30 of that is pure lead. Every year, humanity produces 11 million tons of this heavy, soft metal. Romans used it for plumbing 2,000 years ago. We banned it from paint and gasoline because it poisons children's brains. Yet we can't quit it. Lead stops X-rays dead, stores electrical energy better than any alternative, and possesses one superpower no other metal can match. How does rock containing lead sulfide become the shields protecting radiologists? Why do we mine fresh ore when mountains of old batteries exist? Stay with us. You'll discover why lead is simultaneously essential and deadly, and the shocking secret making it the most recycled material on Earth. 99% returns to use forever.
Our story begins in Missouri's Lead Belt, America's primary source. Unlike flashy gold mines, lead operations look industrial, almost boring. Massive drills bore 800 feet down, following veins of galena, lead sulfide ore appearing as metallic gray crystals. Each ton of ore contains just 3% lead. The rest is worthless rock requiring removal. Underground, miners work in perpetual darkness, drilling blast holes into rock faces. The lead content makes galena unusually dense. Lift a basketball-sized chunk and it weighs like a bowling ball. You feel lead before you see it, explains one miner. Galena has this heft that surprises you every time. Explosives fracture the ore. Loaders scoop rubble into trucks, climbing back to surface through spiral tunnels taking 20 minutes to traverse.
Topside, the crushing begins. House-sized jaw crushers reduce boulders to gravel, while workers monitor from control rooms behind thick glass. Lead dust is insidious, invisible particles that accumulate in bones, causing damage that appears years later. Modern facilities employ enclosed systems, but older operations tell different stories. Walk through a 1970s lead smelter photograph. Workers in street clothes, no respirators, covered in gray dust. Many develop neurological problems by age 50. The industry learned hard lessons about lead toxicity. Today, air monitoring systems track particle counts continuously. Workers shower before leaving. Clothes stay on site. Blood tests happen monthly. One manager puts it bluntly: respect lead or it destroys you. There's no middle ground.
The ore enters roasting furnaces heated to 1,400 degrees. Here, sulfur burns away as sulfur dioxide, captured and sold to sulfuric acid manufacturers. What remains is lead oxide, a yellow powder looking harmless but deadly if inhaled. The roasting building operates under negative pressure. Air flows inward, never outward, preventing escape of lead-contaminated atmosphere. Watch the roasting process through observation windows. Yellow flames dance over tumbling ore. Operators adjust oxygen flow constantly. Too much air, lead oxidizes excessively. Too little, sulfur remains. Getting it wrong costs millions in lost efficiency. The roasted material, called calcine, moves to smelting via enclosed conveyor belts. Nothing touches open air. The paranoia about containment isn't regulation theater, it's survival. Lead contamination cleanup can bankrupt companies.
Blast furnaces reduce lead oxide to metallic lead through carbon chemistry. Coke, purified coal, burns at 2,000 degrees, creating carbon monoxide that strips oxygen from lead oxide. Liquid lead, melting at just 621 degrees, pools at furnace bottom. Picture the tap. Workers drill through clay plug. Molten lead, silvery and dense, flows into molds, creating 90-pound ingots called pigs. The metal moves like mercury, forming perfect spheres when droplets fall. Lead's density is deceptive. A 5-gallon bucket filled with lead weighs 200 pounds, impossible to lift. Ancient Romans made lead pipes by pouring molten metal into sand molds. The same basic process works today because lead's properties haven't changed in millennia.
Refining removes impurities through clever chemistry. Adding zinc causes copper to rise as dross skimmed off surface. Calcium treatment removes silver. Lead and silver frequently occur together geologically. The final product achieves 99.99% purity. This refined lead feeds manufacturing plants producing batteries, radiation shielding, and specialized applications. But here's where the story shifts. Increasingly, smelters don't process mined ore, they process old batteries. Secondary smelters, as they're called, have grown to dominate the industry. Why mine lead when every dead car battery contains 20 pounds ready for reuse? The economics are brutal. Recycled lead costs 40% less than mined lead. Primary smelters struggle competing. Many shut down, unable to match prices of operations running on discarded batteries.
Battery recycling begins at collection centers, where mechanics and scrappers deliver exhausted batteries by the thousands. Workers drain sulfuric acid into neutralization tanks. Each battery contains about 2 gallons of corrosive liquid that can't enter recycling stream. The acid gets neutralized with lime, creating calcium sulfate, sold as drywall ingredient. Nothing wastes. Drained batteries move to breakers, rotating drums with internal hammers that shatter cases, separating lead plates from plastic housings. It's violent. The noise resembles continuous demolition. Lead plates sink in water, plastic floats. Simple physics achieves separation. The plastic gets washed, shredded, and sold to manufacturers making new battery cases. The lead plates, still coated with lead oxide from battery chemistry, head to furnaces for smelting. One facility processes 50,000 batteries daily, enough lead to manufacture 12,000 new batteries.
The smelting of recycled lead mirrors primary smelting, but operates at smaller scale with tighter controls. Furnaces melt battery plates at 1,000 degrees. Impurities rise as slag, skimmed continuously. The molten lead flows into casting machines, producing standardized ingots shipped to battery manufacturers. Here's the remarkable part. A battery recycled today will be back in a new battery within 30 days. The loop is that tight. And that battery will get recycled again in 3 years when it fails, and again and again. Lead never wears out. Its atomic structure remains unchanged, regardless of how many times it melts and resolidifies. The lead in your current car battery might have started life in Roman plumbing, been refined into medieval type, reformed into ammunition, and now cycles through automotive batteries. Lead is functionally immortal.
Lead's history intertwines with civilization's darkest chapters. Romans sweetened wine with lead acetate, called sugar of lead, not knowing it caused madness in emperors. Medieval alchemists poisoned themselves studying it. The gasoline industry added tetraethyl lead as anti-knock compound in 1921, despite knowing its neurotoxicity. For 50 years, automobile exhaust sprayed lead over every city, poisoning children and causing measurable drops in IQ. The phase-out began in 1970s as evidence became undeniable. Removing lead from gasoline represents public health's greatest victory. Childhood blood lead levels dropped 90%. Paint bans followed. Today, lead use concentrates in batteries, radiation shielding, and specialized industrial applications. We've learned to respect lead's toxicity while exploiting its unique properties. The metal that once poisoned Rome now powers modern transportation, but safely, contained, recycled endlessly.
Carbon emissions dropped 72% producing recycled lead versus mining virgin ore. Industry saves $63 billion annually through battery recycling. Processing scrap uses 65% less energy than conventional smelting. Here's the secret we promised. Lead achieves 99% recycling rates, the highest of any industrial material. That car battery has a 99% chance of being recycled properly because it's worth money. Scrappers pay you for dead batteries. Mechanics collect them religiously. The economic incentive creates a closed loop more efficient than any regulation could mandate. From ancient Rome to modern recycling, the transformation completes. We've learned that some materials are too valuable to discard, too dangerous to mishandle, and too useful to abandon. Lead will never be green, but it might be the perfect example of circular economy functioning through market forces. That heavy metal under your hood has been serving humanity for millennia. It'll still be serving our descendants centuries from now, because lead never truly dies. It just waits to be reborn.
Every second, factories worldwide produce carbon fiber threads 10 times stronger than steel, yet 5 times lighter. Picture this. A strand thinner than human hair supports weights exceeding 400 pounds, more than 2 adult humans hanging from a thread, invisible at arm's length. These black filaments, woven into composites, form invisible to radar bombers, Formula One monocoques surviving 200-mile-per-hour crashes, and prosthetic limbs outperforming natural bone. How does ordinary plastic transform into material stronger than steel through fire? Why do engineers call carbon fiber the black aluminum, revolutionizing everything from spacecraft to tennis rackets? Stick around till the end. You'll discover the jaw-dropping reason carbon fiber doesn't break like metal but unravels like fabric, why recycling it became a technological arms race, and the shocking truth about what happens inside furnaces hotter than volcanic lava when atoms reorganize into crystalline perfection.
The story begins with polyacrylonitrile, pan fiber, the plastic precursor looking like white cotton thread. Massive spinning machines standing 3 stories tall in climate-controlled facilities extrude molten pan through spinnerets containing 50,000 microscopic holes.
Each hole, measuring 3/10,000ths of an inch across, thinner than blood cells, produces one continuous filament. Picture spider silk production scaled to industrial extremes. These filaments emerge at speeds reaching 3,000 feet per minute, fast enough to cross football fields in seconds. Chemical baths stretch the fibers, aligning polymer chains parallel to fiber length. This molecular orientation determines everything. Randomly oriented polymers create weak thread. Aligned chains create strength rivaling steel. Workers monitor tension constantly. Variations of 2% cause inconsistent properties requiring entire batches, thousands of pounds worth, to be scrapped. The pan production facility operates 24/7, producing 50 tons daily, enough fiber to circle Earth's equator if laid end to end. Next comes oxidation, the first transformation where chemistry becomes alchemy. Massive ovens, stretching 200 feet long like horizontal tunnels, heat pan fibers to 500 degrees Fahrenheit in pure oxygen atmosphere. Inside these furnaces, oxygen atoms attack carbon-hydrogen bonds in the polymer backbone. Hydrogen burns away as water vapor, leaving behind carbon-nitrogen ladder structures stabilized through cross-linking. This stabilization process takes 90 minutes as fibers crawl through ovens on tensioned rollers. Temperature control matters critically. Too hot, fibers ignite catastrophically. Too cold, cross-linking remains incomplete, causing failure during subsequent heating. The oxidation chamber maintains oxygen concentration at 23% with tolerance of 0.5%. Operators monitor fiber color constantly, watching white pan transform through yellow to dark brown. That color change represents chemical metamorphosis. Polymer becoming something fundamentally different, no longer meltable, now heat-resistant enough to survive temperatures that vaporize aluminum.
Giant carbonization furnaces, operating at temperatures exceeding 3,000 degrees Fahrenheit, complete the transformation. These aren't ordinary ovens, they're inert atmosphere chambers purged with nitrogen gas, creating environments where oxygen molecules cannot exist. Inside this oxygen-free inferno, stabilized fibers lose nitrogen, hydrogen, and other non-carbon elements through thermal decomposition. Only carbon remains, reorganizing into graphite-like crystalline structures. The process occurs in stages. First, furnaces heat fibers to 2,700 degrees, driving off 90% of non-carbon atoms. The fiber shrinks 25%, density increasing as material compacts. Second stage furnaces push temperatures to 4,000 degrees for graphitization, the process aligning carbon atoms into perfect hexagonal sheets stacked like microscopic playing cards. This crystalline perfection gives carbon fiber its extraordinary properties. Processing takes 3 hours, crawling through furnace sections totaling 1,000 feet long. One power interruption, one oxygen leak, and fibers oxidize catastrophically, burning like magnesium flares, destroying millions in equipment.
Now comes surface treatment, electrolytic oxidation creating reactive sites for resin bonding. The carbon fiber, now black as obsidian and measuring just 0.003 inches diameter, passes through electrolyte baths while electric current flows through it. This electrochemical attack roughens the fiber surface at nanometer scale, creating anchor points where epoxy resins chemically bond. Picture this: untreated carbon fiber in epoxy resin slides apart like oiled rope, strong individually but weak as composite. Surface-treated fiber bonds molecularly to resin, creating integrated structure where fiber and matrix function as single material. Modern aerospace composites achieve interface strengths exceeding 12,000 pounds per square inch, meaning the bond between fiber and resin is stronger than many metals themselves. This step is critical because composite strength depends not just on fiber properties, but on load transfer efficiency from matrix to fiber. Poor surface treatment causes delamination, layers separating under stress, the characteristic failure mode making carbon composites unravel rather than fracture.
The sizing application follows, coating fibers with protective polymer layer.
Massive rollers submerge fiber tows, bundles containing 12,000 individual filaments through sizing baths containing proprietary polymer formulations. This coating serves triple purpose: protects fibers during handling, improves resin wetting during composite layup, and provides limited abrasion resistance. Workers wind treated fiber onto spools holding 10 miles of continuous filament. These spools, weighing 200 pounds each, ship to composite manufacturers worldwide. Quality control inspects random samples continuously. Tensile testing machines pull individual fibers until failure, measuring breaking strength, elastic modulus, and elongation. Modern aerospace-grade carbon fiber withstands stresses exceeding 800,000 pounds per square inch, 50 times stronger than structural steel. The fiber stretches only 1.5% before breaking. Steel deforms 300% more. That limited elongation explains why carbon structures crack suddenly rather than bending. No warning, just instantaneous failure when stress exceeds capacity.
After arriving at composite manufacturers, fibers get woven into fabrics or used as unidirectional tapes. Automated looms, programmed like textile machines but operating at glacial speeds to prevent fiber damage, weave intricate patterns. Plain weave creates checkerboard appearance, twill weave produces diagonal patterns, satin weave maximizes smoothness for aerodynamic surfaces. Each weave pattern offers different mechanical properties. Engineers select patterns matching stress directions. Picture this: laying up carbon composite resembles origami, with materials costing $300 per pound. Technicians cut fabric patterns, stacking layers in precise orientations. Each ply orientation, 0 degrees, 45 degrees, 90 degrees, contributes specific strength characteristics. A typical aerospace laminate contains 40 plies, each 0.005 inches thick, creating structures 8 inches thick, yet lighter than equivalent aluminum. Between each ply, workers brush epoxy resin, ensuring complete fiber wetting. Air bubbles trapped between layers become stress concentrators, causing catastrophic failure. So layup occurs in clean rooms, maintaining air purity rivaling semiconductor fabs.
Curing transforms wet layup into solid composite through heat and pressure. Massive autoclaves, pressure vessels 30 feet in diameter and 100 feet long, create environments combining 300 degrees Fahrenheit and 100 psi pressure. Inside these industrial pressure cookers, epoxy resin chemically cross-links while pressure squeezes out excess resin and air voids, compacting layers into dense laminates. The cure cycle takes 8 hours following computer-controlled temperature and pressure ramps. Heat too fast, resin boils, creating voids. Heat too slow, productivity plummets. Modern autoclaves monitor 200 sensors simultaneously, adjusting conditions to within 1 degree and 0.5 psi. After curing, parts exit as rigid structures, material properties now locked permanently. Non-destructive testing using ultrasound and X-rays searches for defects. Even microscopic voids or delaminations require part rejection because carbon composites tolerate 0 defects. Unlike metals tolerating small cracks through ductility, carbon composites fail catastrophically once cracks initiate. That brittleness demands perfection during manufacturing.
This technology emerged from 1960's space race. Thomas Edison experimented with carbon filaments in 1880s for light bulbs. But modern carbon fiber originated when British researcher William Watt developed pan-based process in 1963 at Royal Aircraft Establishment. The breakthrough enabled high-strength fibers commercially viable. Formula One adopted carbon fiber in 1981 when McLaren built the first composite monocoque chassis. Driver John Watson walked away from a 200-mile-per-hour crash at Monza, the carbon tub protecting him despite complete car disintegration. That demonstration convinced aerospace industry. Boeing's 787 Dreamliner, entering service in 2011, uses 50% composite materials by weight. Wings, fuselage sections, tail, slashing fuel consumption 20% versus aluminum equivalents. The B-2 Spirit stealth bomber, revealed in 1989, incorporates carbon composites extensively. The radar-transparent properties, combined with geometric shaping, create aircraft virtually invisible to detection. Today, carbon fiber production exceeds 120,000 tons annually, growing 15% yearly as industries discover applications from wind turbine blades to bicycle frames. Carbon emissions drop by 32% when using carbon fiber in aircraft versus aluminum. Lighter structures require less fuel over millions of flight miles. Industry saves over $68 billion annually through weight reduction in transportation. Wind turbines using carbon fiber blades generate 18% more electricity through longer, lighter blades, impossible with fiberglass. So here's the secret promised. Carbon fiber doesn't break, it delaminates. Unlike metal fracturing through crack propagation, carbon composites fail through layer separation. Impact damage creates barely visible surface dimples, hiding extensive internal delamination, while composites require ultrasonic inspection after any impact. That failure mode makes recycling challenging. You can't melt carbon fiber like aluminum. Heating destroys the crystalline structure that provides strength. Current recycling uses pyrolysis, heating composites to 1,000 degrees in oxygen-free environments, burning away resin while preserving fibers. Recovered fibers retain 70% of original strength, creating secondary markets. From plastic thread to aerospace revolution, cycle completes. Carbon fiber represents humanity's ability to reorganize matter at atomic level, creating materials nature never intended. We've learned to cook polymers in furnaces hotter than volcanoes, aligning carbon atoms into crystalline perfection, stronger than any metal, yet lighter than water. That thread, thinner than hair, doesn't just reduce weight. It enables impossible structures. Aircraft wings spanning 200 feet without internal support. Prosthetics stronger than bone. Spacecraft components surviving forces that pulverize steel. We've engineered the future, one microscopic fiber at a time.